In this video we look at some typical exam style questions for first order systems. So what we're going to do is give a walkthrough of how to tackle some typical questions, and the key mechanism we're going to use is to begin by summarizing clearly what you know about first order systems. So I'll re-emphasize that point. That's what you start with, is by summarizing clearly what you already know, and then read the question. Often the application of core knowledge to the question will be obvious if you've written down that core knowledge first. So here's an example of what that core knowledge might be. If we have a first order system, we've already said that we should use the time constant form. There it is, t dx dt plus x equals some constant times the input. So if your system isn't in time constant form, the first thing to do is put it in time constant form. Now once it's in time constant form, you can write a standard equation for the step response from a non-zero initial condition, and that is given here. You'll notice that the decay rate depends upon the time constant t. So there's t, and you can see t has appeared in the equation here, and if we do a typical graph, you'll see that in essence, in one time constant, I'll mark it here, so after one time constant you've moved 63% of the way to the steady state. And indeed, what we've done earlier is you can also work out things like the gap there is 5% and so on. I'd better remove that because I think that's going to be in the way. Now, you also know that the steady state depends only on this term here, Cu. So there it is, the steady state is given by Cu. So there's the core knowledge, and we don't really need anything else for first order systems. Let's have a look at some questions then. So question 1, the concentration of the product of a chemical reaction is affected by an input F. The concentration can be modelled by a first order differential equation with unknown constants B and D. And here's the equation you're given, dc dt plus bc equals df. So a technician performs an experiment by giving a step change in F equal to 0.005 meters cubed per second. And there's a figure on the next page which shows the response. And your first job is to use the figure to estimate the model parameters. So you need to find the parameters B and D from this figure. Having done that, sketch the expected behavior if the flow is changed from a steady 0.005 to a steady 0.008. And finally, what do you think would be the effect on the behavior of adding a catalyst to this reaction, which increases the rate of production by 0.01 moles per meter cubed? Okay, so here's the figure. You can see that we've assumed that the concentration started from 0 and it's gradually progressed over just over a minute. So the question was, use this figure to estimate the model parameters for this process, and you'll notice it's asked you to get parameters B and D, but there's a problem here. This is not in time constant form. So what did we say at the outset? The first thing to do is go back to time constant form, because that's what you know. So a time constant form for this system would be written like this, t dc dt plus c equals some k times f. So what I'm going to do is I'm going to ignore what they've given me for the time being because it's confusing, and I'm going to say what I know is the time constant form. So let's go back to that. So we get 63% movement in one time constant. So if the overall movement is 0.025, and you can see that from this value here, then 63% movement is 0.63 times 0.025, which is approximately 0.16. So if I mark that across here, then you see we get 63% movement in approximately 20 seconds. So clearly the time constant t is approximately 20, and hopefully you all agree that was relatively straightforward. Right, I'm still on the same theme. We're trying to estimate the model parameters for this process, and so what I'm going to do now is say we know that the steady state is kf. So there's again my time constant form, and the steady state is just given by this right hand side, kf. Well, I can see the steady state, here it is, so I can write that kf equals 0.025, and I've been given that f equals 0.005, so clearly k equals 5. So now you'll notice I've written the same question again where I started. I wanted this model here, which isn't what I've got, but let's have a look and see what we've actually got. So what we said is we know that if we put the model in time constant form, then I can work out that t is 20 and k equals 5. So I can do that easily. All I need to do now is rearrange this model in order to find b and d. So if I look at the model up here, you'll notice the coefficient on the derivative is 1. So I can do that by writing dc dt plus 1 over tc equals k over t into f. And clearly you can see that b equals 1 over t and d equals k over t. So b is going to be 0.05 and d is going to be 0.25. Next part of the question then. Sketch the expected behaviour if the flow is changed from a steady 0.005 to 0.008. So again, let's write down the things we know carefully before we try to start. Initially, we are at steady state. We've got f equals 0.005, so we know what x is. We had that on the original figure. X is 0.025, so that's where we start. Where do we finish? Well, if f equals 0.008, then the new steady state, given by kf, must be 0.04. So I've got a start point and an end point. I know that the time constant is 20 seconds, and I know I move 63% of the way from the start point to the end point in 20 seconds. So what's the total movement? Well, the total movement is 0.04 minus 0.025, which is 0.015. So that's how far I move between the two steady states, and so I can multiply that by 0.63 to find out how much it's moved after one time constant. If I do that, then what do we get? I'm not sure if I've worked this out in advance. I should have done. I'll go back to that in a moment. I think it's roughly 0.9. Okay, so we'll just write 0.9. I can't see where I've written it. So it's roughly 0.95, so we'll just leave it there for now. So next, let's do this sketch. So what we do, we put some axes down. Now you can use proper graph paper if you want, but the key thing is we can have one time constant, two time constants, three time constants, and so on. We know we start from 0.025. We know we finish at 0.04, so I can put some horizontal lines across just to mark those two values. And we know that after one time constant I've moved roughly 0. So that should be 0.95. Sorry, it should be 0.095. That's what happens when you do things on the screen. So after one time constant I've got to roughly 0.034. So I'm going to mark that there and go across. So that value is 0.0345 roughly. So I've got the value after one time constant, I've got the start point, I've got the end point, and you remember that if you follow the initial gradient you get to the steady state value in one time constant. So that gives me the initial gradient. If you want to do 5% offsets you can, but to be honest, within sketch accuracy you're not going to get very far. So our sketch is going to give us something like this. You were only asked to sketch, you weren't asked to do a very precise plot. Okay. So finally, what would be the effect on the behavior of adding a catalyst which increases the rate of production of C by 0.01 moles per meter cubed? So here's the key thing. There's no fixed answer to this. This question is put in an exam to see how students think and to see what they come up with and what their understanding tells us. So if you just ignore the typo, that should say 0.01. So what can we say? Well, here was the original equation, dc dt plus bc equals df, and the rate of production is this dc dt. So if that rate of production is increased by 0.01, just ignore the typo, put 0.01, then the equation is going to change to this, dc dt equals df plus 0.01 minus bc. And hopefully it's clear to you that with this change of model, there is no change in the time constant. So I could rearrange this back into time constant form by writing it as dc dt plus bc equals df plus 0.01. And what you see is that there's no change to the left hand side. If I put this in time constant form, I'm still going to get t equals 1 over b. So there's no change in the time constant. However, there is a change in the steady state. The steady state is increased. So next question. The angular velocity of a satellite dish is governed by a simple DC motor with a model given below. So here's the model, a d omega dt plus b omega equals v. So the operator uses a step change in voltage from 200 volts to 350 volts and finds the angular velocity behaves as in the figure we'll show you next. Use this figure to estimate parameters a and b. And then, due to wear and tear, the system becomes subject to a 20% increase in friction, which causes a drop in steady state gain. Find the new model parameters and sketch the expected behavior for a voltage change from 300 to 180, assuming the system began at steady state. And finally, explain why increasing friction reduces the time constant. So again, what we're going to do is do this one part at a time. So the first part was the operator enters a step change in voltage from 200 volts to 350 volts and gives you the figure you can see here. Use the figure to estimate the parameters a and b. And once more, you'll see that this model is not in time constant form. So what I'm going to do initially is ignore that. I'm going to say, okay, I want to get there eventually, but at the moment, I want to go back to what I know. So what do I know? I know that for a first order model in time constant form, so there's the time constant form, t d omega dt plus omega equals kv, then I get 63% movement in one time constant. Well, the movement, the total movement here is 1.5, and 0.63 times 1.5 is approximately 0.95, and so what you'll see is that distance there is approximately 0.95, and therefore t is approximately 0.5. So I can use this figure to give myself the time constant if I want the model in time constant form. Let's carry on then. So next, what we're going to do is say, okay, can we do something about the steady state? So if the model is in time constant form, again I've put the time constant form down there, then the steady state is given by this term here, kv. Well, I can see what the steady state is here. It's 3.5. So I can simply write 3.5 equals kv. But I know what v is. I'm told that the final voltage is here, it's 350. So I've got 3.5 equals k times 350, which tells me that k equals 0.01. So let's summarise what we've got. We wanted to find this model, a d omega dt plus b omega equals v, and I haven't done that yet. What I've done is I've said, if you asked me for the time constant form model, I can do it. So if you ask me for t d omega dt plus omega equals kv, then I can tell you that t equals 0.5 and k equals 0.01. That was straightforward. All I need to do, therefore, is rearrange this to find a and b. So you'll notice for the model they're asking for, they've got a coefficient of 1 on the v. So if I simply divide through by k, I'm going to get t over k times d omega dt plus 1 over k times omega equals v. And therefore clearly t over k equals a and 1 over k equals b. So a is going to be 0.5 over 0.01, which is 50, and b is 1 over 0.01, which is 100. So you'll see, by first of all concentrating on time constant form, which I know, the question has turned out to be fairly straightforward. Next part of the question then. Due to wear and tear, the system becomes subject to a 20% increase in the friction torque, which causes a drop in steady state gain. Find the new model parameters and sketch the behaviour for a voltage change from 300 to 180, assuming you began at steady state. So the first thing to note is the friction torque term in this equation is the b omega term. And you can also tell that because it tells you that you get a drop in the steady state. So therefore the question is telling you that that term b is increased by 20%. Now the steady state is given by v over b, so you can see in order to reduce the steady state I have to increase b. So it all matches with what you've been given in the question. So what's our new model going to be? Well, b therefore has gone from 100 to 120. It's been increased by 20%, and you notice the numbers have been kept nice and simple for you here. So your new model is going to be 50 omega dot plus 120 omega equals v. So the same model as before, except I've replaced the 100 by 120. Now before I carry on, before I try and do the sketch, you remember that to do sketches we like things in time constant form. So what I'm going to do is put this model back into time constant form. So I end up with 50 over 120 omega dot plus omega equals 1 over 120 into v. And therefore you can see there's my new time constant, and that's going to be approximately 0.42, and there's my new gain, 1 over 120. So let's look at the sketch then. So we've just said that the new time constant is roughly 0.42. The steady state is v over b, and v's gone from 300 to 180. So what you're going to get is, let's check we haven't got another slide, so we'll do it up here. If v was 300, then the steady state was 300 divided by 120, which is 2.5, and if v was 180, then the steady state was 180 over 120, which is 1.5. So what this question has told you is the system has begun at 2.5 and finished at 1.5. So what we'll do is we'll put those two values in here. So we've begun at 2.5 and we finished at 1.5. Now these numbers are actually quite nice because you'll notice the actual total movement is just 1. And what we're going to do next is we're going to say we move 63% of the way in one time constant. Well, 63% of 1 is very easy to work out. It's 0.63. So what I can do now is I can mark 1 time constant, 2 time constant, 3 time constant. I know that I get from the start point or the gradient at the start point gets to the end point in one sample. So there I mark the initial gradient. I know that after one time constant I've moved 0.63, so that's going to take me to a value, I think 1.87, so that's going to be about there. So now all I need to do is get my smooth curve following that gradient through that point, and it's going to do something like this. So there's my sketch. Now if you want to be precise, you'll see I've just put on the x-axis capital T, 2 capital T, 3 capital T. If you want to, you can add in next to that. That's 0.42, that's 0.84, that's 1.26, and so on, if you want to put the actual timescales in there. So finally, explain why increasing friction reduces the time constant. Well, the time constant was given by T equals A over B. So if B increases, then T reduces. So you remember we had A d omega dt plus B omega equals V, or in time constant form, A over B d omega dt plus omega equals 1 over B into V, and so clearly the time constant is A over B. So if B gets bigger, then T must get smaller. And again, you'll see that this part of the question was meant to be fairly straightforward. You could use heuristic arguments that if you've got higher friction, then you're taking more energy out of the system, or you're taking the energy out of the system faster, and therefore the system must slow down faster. Or equivalently, if you've got a higher torque, then you've got a faster deceleration. So again, all these imply that the time constant is quicker. And that's the end.